con aquella, ¿no? Entonces, ¿empezamos o no empezamos?
Sí.
All right, so good evening to everyone. We're going to start with the second session of ONMoS, and with the second session about Wasserstein spaces. My name is Rafael Espínola. I'm professor here at the University of Sevilla, and we are going with Wasserstein, with the second session of Wasserstein spaces. In the first session, I already wrote that blackboard where I recall some of the elements we introduced in the first session, just to recall them. In the session of today, as announced last week, we will talk a little bit about the metric, about the spaces themselves, about the metric, about the topology, and about the geodesics in these topologies when they happen, and a little bit about how the curvature in these spaces may go, right? There are many other things related to these spaces that we cannot reach in just 2 hours. Maybe in the future we could set some other session if people are interested in that. Today the idea is to get to more or less to the concept of geodesic and a little bit of curvature. All right, so this is to recall what we did last week, the main notions. We typically are working on a separable and complete symmetric space, which is a policy space. Sometimes just separable, but in general, separable and complete. We're considering the border probabilities on X. And a very important element in all this theory, we already had the chance to check that last week, is the notion of push-forward measurement. We will be using it a lot. It will show up a lot today too. And we have this kind of change variable with the push-forward measure that also happens in this story all the time. A very important notion coming from optimal transport. The couplings. Couplings also called transport plans, right? Basically, we have the metric space, we have two probabilities in the metric space, and we look for another probability in the product space in such a way that the marginal measures are the two given probabilities at the beginning, right? Imagine that I'm not here too late. Why? Then it's X and X, but in general, would be here because we put them on PX. But would be Y2. The margin on the first coordinate has to be one of the probabilities, and the margin on the other, the push forward of the margin on the other variable has to be the other probability which was at the beginning. And then we have what is called a coupling or a transformer. The set of all the couplings is noted as gamma, capital gamma of those two measures. And we always have, as we showed last week, that set is not empty because at least we have the product mixture of mu and mu, right? That's something very important. Then we will record the layout of optimal transport. That will be later. Then we also work with the narrow convergence and tightness of measures. And that's just as the probability measures are in this dual space, we have a natural notion of convergence, which is the weak convergence. But the weak convergence happens not to be completely optimal for this scenario, as we need the limits to be probability. And so the weak convergence have to be changed into the narrow convergence. Basically, it's the same, but here the test functions are taken not on C0, but the set of bounded continuous functions, right? And that's going to be like the natural convergence in wide spaces. And then this notion of tightness, that is something like a family of probabilities is tight when they are like concentrated, when we can concentrate them, their supports in one compact set for all the elements in the family, right? The notion of tightness is going to be very closely related to the notion of compactness, right? We saw that here was the Prokhorov theorem, right? Says, well, the family is tight if we have this compactness property about the sequence. If all sequences contain a subsequence which is convergent in the narrow sense, right? So that's basically all I wanted to recall from last week. I keep this here for later. And we go back, we get to this blackboard now, and we start with the talk of today. So this would be that's basically what we are going to do now. So we have X, as we said before, separable and complete, and we have a new in this space, and we have like the cost function that now is going to be for P. We're going to have xy, that will be the cost function is going to be pt xy, the distance to the p power. And what we defined pt is going to be the set of all the probabilities on X in such a way that that is a space that we are interested in, this set of Borel probabilities with p moments finite. That's basically the condition. This will show later that this actually does not depend on x0. This set pp does not depend on x0, the election of x0. And we defined a metric on this. We said what we get the definition, we didn't prove it was symmetric, but this is going to be our space. We need the candidate for a metric that was what we call equal to infimum of all these intervals. And we explained last week that actually, if the function c is taken like this, that's it, if we have d to the p, we are in the conditions to assume to know that this is actually a minimum. This is time. Right. So we know that there exists gammas belonging to couplings such that but we know that this infimum is attained. We also have couplings like this, and a coupling like this is called optimal. And we made a note, maybe that's useful. Gamma zero mu set of optimal optimal couplings. Of course, this set of optimal couplings depend on this function. So if we change this function, the optimal couplings doesn't have to be the same. So we don't write the P right depending on this, but it's good to know that this set of optimal couplings depend on the cost function we are considering, right? So that's it. This is the P Wasserstein. Yeah. See it? No. Space is going to be PT X W. That's the Wasserstein space. So what we have to see, is that that's a metric space. But before that, we're not going to write the proofs, well, proofs in the text in general, but we will just give a few ideas about them. But before getting to the fact that this is a metric space, we are going to see two other facts. This is something that we already said last week, is that, P of X does not end on X0. That's very simple because the function f of t is convex of P here. And so we have A plus B into this AP plus BP over 2. And so if we have integral on F if we have another point x1, we consider the same element, the p moment with respect to x1, we can always do this. We can always do that. Considering mu. Yeah. And so we can apply this, and this is so this is smaller than infinity because p is in this space with x0, and this is smaller than infinity because mu is a probability, it's a finite function, right? So this space does not depend on the fixed point x, maybe any other point. And the other thing that we also said last week is that x is that we can find a copy of x into the Wasserstein space for the p. For that, we need mapping p inclusion p x. We just take the delta measure, right? And so if we want to find this value, we will have to do the story of the infimum of we have to do that story of the infimum, knowing that there are elements in capital gamma that that make the infimum and minimum. And what happens here is something that we also said last week, is that actually there is just one coupling from the set gamma mu. Actually, when we are talking, when we are working with delta probabilities, reduces to there is no other element in the family of couplings of those two measures, and so there is actually the integral in x times x between xy in delta x1 times delta x2. And that's obviously that's a product measure we can apply for Vini, and that's obviously distance to p x1 x2, right? And we have that this is an isometry that put x into this other space. So in general, we can expect the Wasserstein space to have nicer properties than the space X. Locally, it may have nicer properties, but in global, since it contains X, it cannot have nicer properties than the space X itself. All right. So now what about the distance being actually a distance? To see that that is a distance, we need to check these three facts, right? First, we have the distance zero only if the two measures and the two probabilities are the same. We can take a look at that one, because it's not that complicated, right? And it's important that the infimum is attained to make this proof work. Actually, what we have is that from here, it implies that there exists an optimal plan, which means integral times x of that means that we have that integral equal to 0. And what it means that the integral is equal to 0, that means that this measure gamma is concentrated on the values where this function is 0, right? So this implies gamma implies that gamma has to be concentrated on that graph. And it's not hard to see that if that is the case, if gamma is concentrated on the graph of the identity map, and the marginal of gamma has to be mu, then it has to happen if we consider this, because we go with a push forward measure, this power, the push forward measure. This is mapping for the push forward measure. Then it has to be I repeat it. Since gamma is concentrated on the graph of the identity map, and the marginal of gamma in the first coordinate has to be equal to mu, it has to be the case that gamma is actually equal to this push forward motion, right? That is not other option. And what happens to that push forward mapping? What happens that we know since gamma belongs to this set, we know that right? But if we work that push forward measure directly on the expression we just found of gamma, this other push forward measure, it happens that that is equal to mu, right? So at the end, what we have is that mu equal to, right? And that will make the proof for one sense. For the other sense, if we start from mu equal mu, we just build this measure, and this measure would make the zero, right? So we will have the two sets. The interesting thing about this proof is that we actually use that that there are optimal plans, optimal topos, right? Next thing would be the symmetry. This is easy. Can use here. This is symmetry. That means we have to prove this. In order to prove that, we will also use the push forward story. We have to consider this map as we consider as right x and x and x. Y set into yx. Right. So we say let gamma be an optimal coupling from mu to mu, right? And we consider main take this solid gamma equal to the push forward measure of gamma through this mapping that change the order of the coordinates. So then we have then easy to see that this actually going it's a coupling from mu to mu. So we have the distance with p of mu the smaller than equal to the integral taking this coupling, means to the integral x and x of the t xy d gamma y. But now you may now we go to the blackboard. Yeah. In this red square, we have this relation. It's called like a change variable. That's what we do here now. We come back to this other one. So applying that quantity, that relation, we can write this equal to the distance x times x of and we change the gamma title with the gamma. We compose P with the mapping S. And what we have we have that, but since the metric itself is symmetric, we have, and gamma is optimal, gamma is in gamma 0, we have this. Right. We have one inequality of the quality we're looking for. The other inequality goes making the same work in the same, starting from the other point, right? Working the same work going from there to here. That would be the same. All right, so we have symmetry. And the most complicated part that we are not going to show in detail is the triangle inequality. All right. And in order to prove this, we need maybe one of the techniques that is one of the most important in all this story. We go to the other blackboard to I don't know if you know about this. It's called the disintegration measure, right? And it's a kind of Fubini theorem. But Fubini theorem works for product measure. We have iterative intervals, and somehow it's natural to decompose that. But in the kind of measures we're working, we typically work on product spaces, and we're taking measures that are not product measures. So, do we have anything similar to Fubini in that situation? Well, we have what's called disintegration theory, or disintegration measure. I wrote here just two situations. One of them would be the most reduced case to a product of two spaces, and basically says what it says here, right? We have a probability in the product space that it have to be a product measure. Then somehow we consider one marginal, that's one, which is fine. That would be like integrating with respect to x or integrating with respect to y. And then we need the other part, which is the hard one. And what we say is in this integration of measures is that then there exists a family of probabilities on the second space on x2, right? In such a way that we can do this, right? It's like we integrate with respect to the set of probabilities in x2, and then so we integrate it with respect to the marginal of the big measure when we project it on the first coordinate. Right? So it's a kind of meaning without not for product measure. And this technique, it works for building the kind of measure that we are going to need when we work with convergence of sequences, or when we work, for instance, in this case, with the triangle inequality. Is that in general, we have a sequence of a space, we can consider it the cardinality of the natural number. We have the probability in each one of those spaces, and we have a coupling from, well, these are the two cases that are related here because are the most typical one for the kind of situation that happened, right? The probability that goes from one probability to the next one, I mean, a coupling that goes from one probability to the next one, and a coupling that goes from the first probability to the I probability. Okay. And then what it says is that we can, if we consider the space of the product of all the xy, we can find probabilities in that big space such that the marginals behave very well for our purposes. I mean, this probability, if we consider the marginal for the coordinates y and y plus 1, then we find the coupling we were working with at the beginning. If we consider the marginal in the coordinates 1 and 9, then we find this other coupling that we have to begin. So that's what makes possible to solve that kind of problems in this theory, right? That we start with with couplings joining two probabilities, and we want how do we join different couplings from different probabilities? That's the way, right? We look for these big measures in the big space, and then the marginals are going to be the coupling we have, and then that's the way we find the limits, or we find some other things. In this case, we get back to this blackboard, right? In this case, applying what I just showed there, would be reduced to a triangle inequality in an LP space of the large measure. I write it here just very fast. From what we saw, from what we said, if we take gamma 1, 2 optimal, mu1, mu2, and gamma 2, 3 optimal from mu2, mu3. Then from what we just saw, there exists probability here such that P12, the projection in the first and second coordinate of gamma is equal to the coupling, P23, well, we can write here, right. But we can write that. The different marginals, probabilities of this measure are the couplings we had. The couplings, yeah. We always have 2, 3. Yeah, we have couplings for all the measures, taken 2 by 2. That's the point. And so, and it happens actually equal and it happens that we have that relation, or anytime we write here y and j in 1, 2, and 3, right? And at the end, what I said before, this inequality becomes an inequality in LP of this space, right? P, X, 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 using the usual family, right? And that's what we are doing. These numbers here are exactly so a number, then it follows from the triangle inequality in this space. It's very well known, right? So the triangle inequality really requires this integration theory, which is a strong tool in this field. All right, so I'm going to comment next, without proof, some facts about the topology of these spaces. This what's really fast just to close. One of the things is that the metric space X is inside the Wasserstein space. And one of the interesting things about this space is that actually that has a big impact in the topology and the geometry of the Wasserstein space. In particular, we can wonder about if these spaces are separable, if these spaces are complete, what about the compactness, and things like that. Well, for the compactness, we have something like this, COM, in relation to the compactness, says 1 sequence probability in here, and one probability in here. Then we have equivalence here is that mu n is convergent with respect to the metric mu. The other one, well, actually, the convergence with respect to the metric is going to be very close to the weak convergence of the narrow convergence, right? The weak convergence, but for the weak convergence to work well, we need to add some mass conservation. This is few moments. And the convergence of the p moments, right? And it happens that the sequence convergence with respect to the metric in the Wasserstein space can be written in terms of the weak convergence in this other way. We're not going to prove this. The proof of this requires the Prokhorov theorem. It's not that hard, but to take time that we don't have. Then, which other facts do we have? Zero. Put the right hand all at once. Well, we're assuming X is a parabol. That space also is a parabol, right? We are always assuming X is a parabol. The part of X being complete is not always assumed. I mean, it may be, it may not be, depending on the properties we want, because the theory works with X separable. But separable, we always have to assume for things to more or less work. The then set we have here. Actually, this is a consequence of this characterization. The then set would be the convex combination with rational coefficients of beta delta mu on points in dense and numerable subset. That would be the set that makes it worth to prove that this space is a problem. Right? If X is complete, we have to assume X is complete equally. Could not be the case. If X is complete, then and for this, the proof requires the disintegration theory. And here you have to take the infinite product of spaces, right? Not only 2 or 3. Another thing. Set probabilities in here is relatively compact if and only if is high and P uniformly integral. Which means that the few moments of P elements of A are bounded. That means a bound for all things. All right. We have more or less that. We could guess this from the Prokhorov theorem. And what about the compactness? Well, the compactness also basically follows from here. If we suppose X is compact, what we have is if X is compact, P of X is compact too, is very simple. This is already written here. And then if P of P, P of X is locally compact, this may be how surprising, but it's the case, then X is compact. So we can say that if this space is locally compact, then it has to be compact. Because if this space is locally compact, X has to be compact. And if X is compact, this space is compact. That's the situation there. All right, so this is main facts about the topology. Maybe the most complicated one to prove is this one. And it's about Prokhorov theorem, tight properties of probabilities and things like that. With that, we can go to the geodesics. Maybe it's a part that we may enjoy a little bit more. This one. Geodesics. If we have geodesics, we can start thinking about segments, and we can start thinking in a natural way about convexity of mappings and things like that. We can also, we also have triangles, and if we have triangles, we can wonder about how thin they are, and we would be talking about curvature of space. So let's see how we find the geodesics. And then we will talk a little bit about the curvature of the first insights about the curvature of these spaces. Geodesics. This, we may think X being separable and being complete is also geodesic. Well, first, the notion, well, a geodesic segment. We can write the definition. It's a constant speed geodesic. So we have C mapping that goes from 0, 1 to the Wasserstein space. It's going to be, we denote C of T, E of T, right? So is a constant speed geodesic. From into 1 if the Wasserstein distance or two of those probabilities in the tree happens to be equal. It's the natural definition for geodesic segment, right? Here, CMS. So the idea is, can we find this kind of truth in Wasserstein spaces when X is geodesic? Right? So geodesic space. Geodesic space would be basically this. If we have 2 points in the space, we can find a segment joining them, right? And the answer is going to be positive, and we're going to show now how those geodesics are built.
Yeah. All right, so we are going to consider PT. Say, consider PT. It's a new kind of projection, but now it's different from X into X, but XY is taken into 1 minus Tx plus Ty, right? If we were in a linear space, this makes complete sense. If we are in a geodesic space, then we have to choose first a segment joining these 2 points. In case of the geodesic space, it's not uniquely a unique geodesic space, and then this will be just a point. I mean, it's more typically within the context plus like that, but it works the same than if we were in a linear space. So we may think we are adding vectors, right? We consider that mapping, and from that mapping, and consider mapping PS T to go from X and X to X and X, and XY set into P plus XY and PT XY, right? Mapping. And then here, of course, SMT 01. So we have elements in the segment. Then we denote UT equal to this push forward measure. We haven't said what's gamma, right? All right, so we have to set first gamma. So yeah. So take mu0, mu1 in P of X, right? And what we're going to do is to build a geodesic segment and speed content speed geodesic segment from mu1 from mu0 to mu1, right? So if we have these 2 probability measures, we know that this is an optimal plan. Let gamma 0, mu0, mu1. Yeah. And then we have P0, push forward measure P0 of gamma will be mu0, because it's a coupling. P1, push forward measure will be of gamma will be mu1. And before, if we put here the parameter t as the number from 0 to 1, to have this measure is denoted mute. Right. Continue up here. So we have this. We have gamma optimal plan. We have 2 probabilities that we want to join, right? With a geodesic segment, right? So now we say let for S and T in the interval 0, 1, let ST equal the push forward measure right. This is the pair of mappings pi s pi t. It's just mapping from x 10x to x times x. So we would have a measure like that. It will be a measure in x. This belongs the probabilities of x times x. right? So, what will be the good thing? The good thing is that this probability that we have written here is actually a coupling. It's actually a coupling from mu, we have mu t, from mu t to mu s, and that's what happens, right? It's easy to check. We're going to check it like this. That's what happens. Then also Ps of gamma sp is equal to mu s, pt before gamma st is equal to mu t. So what we have is that actually this, so gamma st belongs to the family of couplings between those two measures, right? All right, so basically what we are showing is that these probabilities are actually the points in the US example that we want to show. Now, what about the distance of these two probabilities? We have since it is the infimum of all the integrals with couplings integrating with respect to couplings, we can say that this is more or less equal than if we take that integral with this particular coupling. The integral x and x into p x y gamma t x, right? We have that, right? But now we know that this is a push-forward measure. It's a push-forward measure of this. So applying against the change of variable like formula for the push-forward measure, we can rewrite this integral as the integral x and x, which we have to compose this with this mapping. So what happens is we have here Ps y pt y, and now we have and now this is very simple because it's very simple, yeah, because these pi s are actually this convex combination, and these are convex combinations these are like 2 points in the same segment. So it's like if we were working in a real segment, which means that actually this is equal T minus S with P. Next. So it's equal to T minus S to P integral x times x d to the p squared d gamma squared. But gamma was an optimal coupling from mu0 to mu1. So it is actually equal to the distance to the p power mu0. Right, and in that way, what we have seen is that we have this this relation. That this distance, the distance between these two measures, these two probabilities, is lower than or equal to this, right? But actually, what we are looking for is that that's an equality, because it's like 2 points in the geodesic. Right? It's like we are at the end, we are in the geodesic. This is mu0, this is mu1, this is a geodesic. So if this is mu s and this is mu t, then the distance between these two has to be actually this, right? Has to be t minus s times the distance of the big sign, right? So we need an equality And it would be very surprising that we have a strict inequality here, because that would be against the triangle inequality. How we make that inequality is very simple. Because yeah. That's now equal to mu p mu 0 mu s. We assume x is more than t. The p mu s mu t plus u t mu t mu. And if we apply what we have shown to these three distances, what we have is that is smaller than or equal to s times p mu 0 mu 1 plus t times s times p mu 0 mu 1 plus there will be 1 minus t, right? Actually, it's equal to. So we start from here. This is smaller than or equal. It's smaller than or equal. This actually, yeah, smaller than or equal. At the end, we get the same number we had here. So all these things have to be equal. And so we have that is actually an equality. And so we have that the family vanish with C from 0, 1 to p of x, assuming mu p, as before, is a geodesic segment of constant speed, what we were looking for, right? So when the space X is geodesic, has geodesic segments, we have geodesic segments in the Wasserstein space. Now, I would finish soon. We already have an hour, but I would finish soon because it's just a couple of details that we have left. What is something interesting about this geodesic that we just found, that we just constructed, is that actually it's like we did, it's like we took mu 0, mu 1 here. We took gamma, not optimal green, and the geodesic was constructed out of this gamma, right? So we had these families of mu t millions to 0, 1. There is from. So the question is, if we have an optimal transport on one hand and another optimal transport in the other hand, we have two geodesics. Are they going to be the same, or they are not going to be the same? It's going to be a question. The problem of when optimal transports are unique is a very important question in the theory, and under certain conditions, it happens to be the case, but it's not the case in general. So let's look at two facts on geodesy. One of them, I'm not going to give any detail on why it is true, but it's true is that in general, or what you should expect from a geodesic in a Wasserstein space, I mean, you have to look for very strange examples for not having that. Is that, you know,
geodesics do not branch. That means that if you are working a geodesic, that geodesic cannot break into two ways being a geodesic. X, Y, Z is like, this is a segment, and this is a segment. So the geodesic is like, it branches as geodesics. It would be called the branching point, right? And where this branching geodesic happens? These branching geodesics are associated with R3s, right? Are very common in R3s, are associated to CAD. If we are talking of CAD space, it would be CAD of curvature minus infinity. And also it happens that if X has curvature fold below, then it does not have branching. Does not have branching geodesic, right? So this is saying somehow that, or it's pointing in the direction that if we are worried about the curvature of Wasserstein spaces, maybe it's going to be the case that they have to have a kind of inferior bound. Now, another fact that it also points in that way is that actually it's relatively easy to find points that are joined by more than one than just one geodesic, right? I will give a little detail on this. This is, but before that, if we think about the spherical geometry, that what happens, for instance, if we think in kappa spaces, this would be the cat1, the cat1 space, the sphere with the metric. That happens in kappa spaces with curvature larger than 0, right? This with K. It would be this cat1 not cat1. It would be with bounded below. I don't remember how the bar not it works. Curvature greater than or equal to 1. If we consider this sphere, this is space with constant curvature equal to 1. In this space, we can take diametral points. We find two geodesic segments joining them. In fact, we always have geodesic joining them, local geodesic joining them. But if we take two diametral points, we have segments, two segments joining them. What it basically means that if, or somehow, that if this is the normal situation, if we have more than just one segment joining those 2 points, maybe that's also pointing in the direction that these spaces may have some kind of a spherical geometry, right? When happens this, that's not going to happen always, but if X is not the geodesic itself, then there are always -0, -1 in here, joined by more than just one geodesic, right? For instance, in this way applied for the Wasserstein space when X is equal to R or X is equal to a segment in R.
But when the space itself is not a geodesic, that means that it does not restrict to a dimensional one set, like the real line is not isometric to a segment, to a real segment of the real line, then we always find that kind of things, and that's easy. It shows an example. Because when this happens, if X is not a geodesic itself, then there exists always 4 points like this. If the space like this is not a geodesic itself, then we can always find 4 points like this. If X were a geodesic, that wouldn't be possible because we would have a geodesic, we have Z, we have Y, and at equal distance from these 2 points, we always find one single point. Right? So it is clear that when we have a geodesic, that doesn't happen. Showing that when the space is geodesic, but it's not a geodesic itself, then we find those 4 points not that hard, but well, it happens. Then we'll complete from 1/2 delta X plus 1/2 delta X prime to 1/2 delta Y plus 1/2 delta Z are optimal and lead to equal geodesic segments. Right. So every time the space is not a geodesic, then we cannot expect to be cat zero. Right? Because cat zero spaces are uniquely geodesic. Could be cat one, right? Could be of constant curvature equal to 1, right? Well, with this, basically, my presentation of today is finished. Yes, there is one other result that goes also in this direction, is that what is known, for instance, if X is a cat zero space about the Wasserstein space. But in general, we cannot say very much. I mean, there are not many things that go from the cat zero space to the Wasserstein space. But well, that's something that's being studied now, and there are some work showing that although they are thought to be cat zero, for instance, they still have some properties that that happen in cat zero spaces, and they enjoy that kind of properties. And also, maybe the most significant result in that direction would be this one. If X taken by space then P2, if we consider the parameter d equal to 2, if the corresponding distance has is a positive curve space. What does it mean being positive curvature curve space? It may mean many things, but because we at certain times this of working with synthetic notions of curvature may allow different options. But this is a very analytical one, because remember, if we are in a curved space, which is curvature equal to 1, the flat space, from the well, we have the parallelogram. From parallelogram quality, we have this. Yeah. Yes, should be. typical one. 1 plus half is equal to 1/2 square is 1/2 square minus 0.4. Right? That's being flat. That's being curvature constant equal to 0. Curvature of being non-positive. One of the definitions would be something in a general geodesic space. Would be something if we have x, we have y and z, and we have here m of t a geodesic, or t a geodesic joining y and z, then it would be something like a square of x to ct, so that is less than or equal to 1/2. And half of t or 1 minus t, depending on how we calculate the cube. From x y plus t is the square of z minus t minus t is the square of y z. Right? That would be an analytical condition for a non-positive curvature space. And for a positive curvature space, it's the same, but we have here the lower than or equal, right? And that's what happens if x 0 positively curved. Right? So all those insights showing that these spaces may have the curvature boundary below, they became very clear in this situation. We need the space to be here, and we need the parameter p equal to 2. As I said in the first session, the most common cases are 3 for 1 and 2. And basically with this, I think I'm done with this presentation. So if you have any question?
Yeah,
Well,
I have a question. Rafael. Thanks for the really nice presentation.
Thanks a lot.
Really clear. So I was curious about your comment about Wasserstein spaces being what, cat 1 or?
Well, no, I didn't say being cat 1.
Okay.
I just said that of having multiple geodesics joining points is very common in cat 1. Well, not in cat 1, but in spaces for curvature boundary below with a number larger than 0. I mean, it would be, for instance, this sphere that has constant curvature equal to 1.
Yeah. Okay. So yeah. Okay. So is it known? Suppose we're looking at the Wasserstein metric with the x just being a Euclidean space.
Mm-hmm.
So you're saying the Wasserstein space might not even be a cat space for that, or?
Yeah, sure. No, I mean, in general, what the last thing I said is that they are positively curved. So they would be I mean. If you want to see them as a kappa space, the kappa would be positive, but we should look at them as a kind of kappa space, but kappa space is a space with curvature bounded above. We should look at those spaces as spaces curvature bounded below.
Well, just because I'm wondering, so I mean, I know that in kappa spaces you can restrict the diameter of the space.
But kappa is positive, yeah.
So that kappa is positive, so that you can preserve the unique geodesic property.
Yeah.
Is there a chance for some sort of restriction for Wasserstein spaces?
Well, the situation is that we maybe thinking this space is that close to the cat-kappa space is not a good idea. I mean,
Okay.
maybe the idea is that these spaces have some properties related to the curvature when we start from nice conditions, and well, as we saw from the example I said, you can take the 2 points. I mean, I wrote this example with yeah, I wrote this example.
Yeah.
Actually, here you can take this point as close as you wish. So
Any,
in
yeah,
spaces,
okay.
yeah. So in these spaces, you wouldn't have that story that if the points are close enough, then there is a unique geodesic.
Yeah.
These points can be very close, and this probably is maybe very close, and then.
Yeah.
So I think it's not, the idea is not to think this space as cat-kappa spaces, but just that under certain conditions, we may consider some curvature property.
I see. And then on this slide, on this board, you have, I was wondering, you're saying that there won't be unique geodesics. Is it known that there are infinitely many geodesics, uncountably infinitely many? Or is it known how many geodesics there could be?
Well, that depends on the space. That depends on the conditions you are considering. But I think in general there are not that many, because in general when they look for optimal plans, the set of optimal plans is not very large. And the different geodesics are related to different optimal plans.
Right, right. And so I guess what I was thinking, so if
sorry, I would say that in general, you are probabilities are going to be joined by just one geodesic segment, but for certain points, you're going to find a few.
A few, yeah.
More than one, but maybe not that many. But this depends on, I mean, we are working on very general setting, just X, a separable space. Maybe if you fix and start working with X and Euclidean space, there are many works about the geometry of Wasserstein spaces with when the space is Euclidean and p equal 2, trying to find that kind of things. Yeah.
Is there a notion of, amongst the set of optimal couplings, is there a notion of extremal points within the set of optimal couplings?
No, as far as I know, there is not something like that. Basically, they try to look to understand when the optimal transport are unique. That's something that No, as far as I know, I don't remember to have seen something about optimal points or things like that. And that's it.
Okay. Well, thanks. Thanks a
lot.
Okay. Excuse me, I have two questions. Excuse me. The first one is about, again, the geodesic property. So is it true that if the underlying metric space X, if X is uniquely geodesic, then the Wasserstein space are uniquely geodesic?
No, that's not what I said. No.
No.
Well, that's what I said. X is a geodesic itself. I mean, this is very clear. This answers your question. What is written here is that when X is a geodesic, it's itself. It's not that it is a uniquely geodesic space. That's, I mean, I try to put it here. I mean, anytime that the space is geodesic, and we don't care if it's unique or it is not unique, then we're going to have a non-unique geodesically Wasserstein space. At least the space X is either isometric to the real line or a segment in the real line, right? So if you, for instance, consider this, that's not going to be a uniquely geodesic space. But if you consider this, but I'm writing two because it's the most natural one, right? P, then this is going to be. But just because the space is not geodesically, I mean, the condition is that the space itself has to be a geodesic If you have, it is a space with more than just one geodesic space, and then you have the situation of those 4 points, and the Wasserstein space wouldn't be unique geodesic. About this space has been very much studied by people walking the geometry on these spaces, and this space exhibit very exotic properties about the kind of properties they are looking for. I mean, although this may seem simple, more simple than some other spaces, it's an extraordinary one.
Okay.
Yep.
Thanks. And my second question is, I read from some literature that the Wasserstein 2 space actually admits a pseudo-Riemannian structure. Do you have any information about that? How to define a local metric on the analytical tangent space at each point on Wasserstein 2 space?
I don't understand the question. If I mean for p equal to?
Yeah, I said I read from some papers that the Wasserstein 2 space actually admits a pseudo-Riemannian structure.
Yeah.
Do you have any information about this kind of structure, such as how to define a local metric at each point on the analytical tangent space?
Well, I know there are some works in that direction, but I wouldn't be able to explain nothing about that right now. I mean, the theory of these spaces by now is quite large, and we would be talking about many aspects or topics. I mean, if you are interested, I could prepare another session for more. I mean, when the sessions that are programmed by now are over, talking about some convexity relations or convex functions in this space, how to deal with the geodesics in that case. I mean, there are many topics that have been developed from these spaces, but I couldn't talk right now about what you're asking.
Okay, thanks, Steve.
Thanks to you. Yeah.
Okay, if there is another question, then I hope you will spend a nice long weekend. At least in Spain, we have a long weekend. In Sevilla, actually a very long weekend, because next week is fair.
It's Feria.
It's Feria de Sevilla. So our next section will be, I think, the 14th of May. The speaker is Justo Puerto. We will send you the link, okay? So, good evening to everyone.
Thanks a lot, everyone.
Renato, if I could grab your ear just a few seconds before you shut this down.
Yeah.
So yes, can you? We were waiting to send